Okay, so what I'd like to talk to you about today is the idea of modeling nonlinear data. And prior to watching this video, if you're watching any other ones, we've talked about we have maybe a scatter plot of some sort. We suspect the data looks like it would be modeled well with a linear function. And we've used the calculator to find a line of best fit to model that data. So the question today will be, what if we create a scatter plot and the data we're looking at is distinctly nonlinear? Okay. So we start with a set of data. It's already in the calculator here. List 1, you'll notice these numbers. It's like 1, 2, and 4, and so forth. List 1 is actually the years since 1971. And list 2, this number, 2,250, this list represents the number of transistors in an average size computer chip during that year. You might be familiar with Moore's law. He had something to say about the number of transistors we can expect. He anticipated that we would see the number of transistors inside of a computer chip, or processor that is, double every 18 months or so. So I guess we'll see how well Moore's law does in this particular case. All right. Well, first thing we should do is take a look at a scatter plot. So to do that, you do second y equals. You go to stat plot. Here it is. It's already selected. We have that plot on. We've selected a scatter plot and list 1 and list 2. Press zoom 9 and get a look at this. And it might not be obvious what we're looking at, but if you make this a little bigger, it's tough to see, but if you look, here's a data point, here's a data point, here's a data point. You start to climb a little bit towards the end here. There's also some kind of curve on here that seems to fit things pretty well. I don't know how that got there, so we're going to get rid of that. We're going to go to y equals. We'll get rid of that equation. And if you're remembering it, I guess there's no harm in that. Something might seem familiar later on in the video here. All right, so anyway, here's your picture. And you can tell that the red dots do not seem to follow the pattern of a line. Okay, so what do we do? Well, it turns out there's a couple of different things we can do. Today I'm just going to study the idea of what's called an exponential regression. We're going to attempt to linearize this data because we know how to do linear regressions. The calculator has a function for that. There's also a mathematical computation for doing it. That would be, that'd be another video to watch. But you can actually do it using some algebra and things. So what can we do here? Actually, what we're desiring to do is take this data and transform it somehow so that it looks like a linear graph. So here's one thing that statisticians sometimes try. Go to stat edit. We're going to go to list 3. And on the top of list 3, we're going to press the log of list 2. What we're doing is we're taking the logarithm of all those y values. And we're going to create a new scatter plot. We're going to create a scatter plot that compares list 1 to list 3. So we'll do second stat plot. We're going to go down here. We're going to go to y list. And we're going to do second 3. And there we go. We're going to press zoom 9, and we're going to get a new picture. And surprise, surprise, this new picture we have certainly looks like a line. So let's take a look at that. You can almost see a line of best fit would go through there very nicely. It's important to remember, this is not the original data set. We have x on the x-axis, but we have log y going up the y-axis. Now, just go back for a minute. Here's the original x versus y. The original x versus y, this looked distinctly nonlinear. And I stated the goal. The goal is, can we transform our data in some way so that it begins to look linear? And we were able to do that. When we took the log of y and we graphed it versus x, we saw a linear pattern in our points. It looks like a positive association and so forth. Now, what's good about having a linear pattern is that I can fit a line of best fit, a least squared regression line, to this data. And that's what we're going to do now. Go back to the calculator and press stat calculate, number 8. And I want to go list 1, comma, list 3. I just typed list 2 by mistake. See, that's a popular mistake. But I really want to do list 3. Because I just showed in the picture that it was list 1 versus list 3 that seemed to look like a line. So I hit enter. And I look and see what I've got here. And I've got some pretty impressive things. And what I'm looking at is particularly that r and that r squared. Look at your r value, 0.997. That means that the line fits this set of data very well. R squared, the coefficient of determination. There it is right above there. 99.4% of the variation in y could be explained by x. Okay, so far so good. What we want to do now is just sort of finish up, really make sure that this line fits the data well. And to do that, you should always check a residual plot. Remember, if R tells you that the line fits the data well, that doesn't mean that the data is best modeled with a line. What you want is a random residual plot to show you that we're not looking at a small section of some larger curved trend. So here's what we'll do. We'll go back to stat plot, and we'll hit enter on the first plot. And here's what you need to remember. Every time you press linear regression in this calculator, it creates a new list of residuals. To find that, you do second stat. Usually it's the seventh thing on the list, but look for it. It says RESID. Here it is, resid, enter, and then just press zoom 9. And here we go. So there is our residual plot. And these look pretty good. Some people might argue and say, hey, there's like a slight curve trend here maybe. Maybe it'd be nicer if there's one more point down here. But that would be a debate. I would say that these residuals look pretty random. And since they look pretty random, that means the line fits our data well. OK. So I'm going to go back to our linear regression output. And what we could do now is we can write our line of best fit down. But just be careful. Because while this says y equals a plus bx, we know it's not really y values that we're graphing. We graph the log of our original y value. So write log y hat like that is equal to 3.217 plus 0.144x. I'm not surprised that slope's positive for two reasons. R is positive, and when we looked at the scatter plot of x versus log y back here, it had a nice positive association. OK, so here's the thing. I really don't want a good linear model for my transform data. What I really want is a good model of some sort for my original data. I want an equation that has y equals with some function of x. That's what I'm really hoping for here. So it turns out what we can do is we can inverse transform this data. We're going to perform something called an inverse transformation. Okay? In order for you to do this correctly, you need to remember something or know something about logs. So here's something that you can try and do on your own. Try typing in something like this to your calculator. 10 to the log of, say, 100 power. Okay? Now, actually, before you type this one, you could probably do without a calculator. You actually know what the log of 100 is. Log of 100 is equal to 2. And that's because when you write log 100 on a piece of paper here, what you're really saying is, first off, you don't put a base. It's really a 10 there. You're saying, what power did I put on 10 to get 100? That answer is just 2. OK, so this becomes 10 to the 2 power. Well, that's just 100. So notice this complicated expression. Notice the two things are just underlined. OK, let's go to the next example. This is where you're going to have to listen very carefully. All right, so 10 to the log of 7. When you think about the log of 7, you went over here and you went over on the side and you said, OK, log of 7 equals something. You'd have a big question mark in your mind, most likely, because this is really saying 10 to some power has to be 7. Now, I do not know the answer to that offhand. Some of you may know it. I doubt it, though. So I am just going to resolve this. I'm just going to say, hey, wait a minute. Log of 7 is equal to this power I put on 10 to get, sorry about that, 7. Well, I don't know what that is, but I know it's the very special number that if I put it on 10, I'll get 7 as an answer. Well, I am putting that number on 10. So 10 to the power I have to put on 10 to get 7 is just 7. You might want to pause for a minute and think about that. So I'm going to use that fact with my resquared regression line. Basically what I'm saying is in general that if you have 10 to So the log of something, it's just the something. Just one restriction here, x has to be greater than 0. That has to do with domain of the log function, which you may remember from your pre-calculus classes. Okay? So this fact right here, I put a box around it, put stars next to it, is the key to performing the inverse transformation. Here's my line of best fit. I'm going to take this to a new page. And we're going to inverse transform this thing. Here's what we're going to do. I'm going to do 10 to this power, log y hat. And if I do that to the left side, then on the right side I have to do the same thing, 10 to this power. Well, we know, because of what we just discussed, that this is really just y hat. And over here, I'm going to use another thing that you probably know about and haven't thought about much lately. All right. So a long time ago, you learned how to do things like this, like x squared times x to the third. And you learned that you could just add exponents in that situation. If you add x to the a times x to the b, you'd get x to the a plus b power. Well, most of your math classes, you went this direction. It was always what you meant to simplify. If you had two bases that were the same, add the exponents when you're multiplying them. Well, you've always had the ability to go backwards if you wanted to. You might have thought at that time you would never really want to. Well, now you do. So take a look at what we can do with this expression. We can make this as 10 to the 3.217 power times 10 to the 0.144x. Okay? So that is using this rule I wrote over here in green in reverse. Here it is. It's this rule right here. I just used it, but I went backwards with the rule. Okay. One more fun rule that you can remember from your past. You learned that if you had x squared to the third, that you multiplied exponents. Or if you had x to the a to the b power, that was x to the ab. And again, you usually went that direction with the relationship. But you've always had the right to go backwards. So here we go one more time. Here's the next step. Y hat equals 10 to the 3.217 times 10 to the 0.144 to the x. That's using this rule over here. Okay. So, turns out 10 to the 0.144, I can figure out what that number is, and I can also figure out what 10 to the 3.217 power is. So we get y hat equals 1648.16 times 1.393 to the x power. And that is called an exponential equation, which you've also studied, or an exponential function, we'll say, in your pre-calculus classes. They're of the form y equals a times b to the x. And it turns out that after we fit the linear regression to the transformed data, we used this inverse transformation method, and we got this equation, which is exponential, which means our data is going to be modeled well. In other words, x versus y would be modeled well with this equation. So what we're going to do is we're going to finish off by typing that into the calculator and seeing what happens. So let's go back to y equals. We're going to go to y1. It was 1648.16 times 1.393 to the x power. Hit enter on that. Here's our equation. Let's go back to our stat plot and go to the y list. Set it back to L2, so we'll do second 2. Enter. Zoom 9. And here you go. You see your original scatter plot and this exponential equation go right through the data. So that's the basic gist of it. Okay, when you have nonlinear data, one of the things you might try and do is graph x versus log y. There'll be other options in the future that will yield different kinds of equations that aren't exponential. We'll discuss those later on in a different video. For the time being, this is a good way to start. Okay? Thanks for watching.